Hello everyone, my name is Deepak and I'm a research scholar at IIT Patna. I am presenting the part of my research work in, uh, through this poster presented in RSD 2024. Uh, so this work is dedicated to the patients who suffers from the epilepsy. And if we see in the data a patient who suffer from this, that is like around 970 millions across the world. That represents 1 out of every 8% are suffering from this kind of disease. So to address this disease, we have uh, used an EEG signal, that is basically electroencephalograph signal that is captured directly from the brain, and these signals provide uh, critical biomarkers for the seizure activity. Okay, so if you see, then in figure 3, that this is the two signals that is captured from the a healthy and non a seizure mm, person. So the first one is a signal from the normal, and the second one is from the seizure signal from the patient. So these two signals identifying the seizure and non-seizure is a very difficult task uh, for patients who suffer from this, because they don't know when or at what time and which situation it can occur. It can this activities get triggered at any time. Maybe some person in some doing some work or anything. So this is very dangerous. Creates some severe disease, severe creates some severe activity. Some kind of it's a voluntary activity, or some person may fall down. So different kind of situation maybe affect patients whenever this is activity occur. So my approach is to use these EEG signals and proposed a automated device that can alert such patients before during the seizure, so that it can the patient become active or conscious before it happened. So to solve this, we have uses a uh, uh, deep learning model uh, uh, to detect and classify the disease. So here you can see in my proposed solution, first we have used an autoencoder that is having a 6 layer of convolution and deconvolution layers. So basically this is the first stage where we take the signals directly from the device, and we perform the denoising activity. um, and signal may get contaminated with the various kind of noises like eye blink and muscle artifact, ocular artifacts, power line, and etc. So this stage, based on a tone encoder, remove the unnecessary noise. Then after the basically pre-processing a stage, and then after this the signal get denoised, and we feed it to a normal two-layer based CNN model that is trained with the some seizure based datasets to give the output result as a seizure non-seizure. So basically and this is deep learning model, and what our target is, as I explained in beginning of this slide, that we are developing this for the wearable devices, so that uh, so then the main challenge is to basically deep learning based solution is very heavy in their mm, mm, size. So it will create very problem when we are deploying this model on some certain microcontroller or edge-based devices in a wearable devices. So this should have a not only lightweight, but uh, that should consume a very less memory on devices. So to do that, what we have applied in a compression technology, which takes these models and compress it to the and compress, and by doing compression it makes this model compatible to the low power, low cost devices that get fitted in the wearable applications. So 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 here in the result section you can see this is the performance of the our model. So the first two columns represent the denoising performance, like uh, noise and PRD value and RMSE based. So and here we have an result for the detection accuracy before compression and after compression. So that's near around 100%. Uh, and the in the table 1 you can see we have an compression results for this autoencoder. uh, so it was originally it is near around 1 million parameters, and then we did after compression we have reduced it down to the uh, 8 lakhs and on something. So it's near around 24% of compression. uh, okay, now you see here in table 2 we have compared this work with the existing work. And if you see in the future improvement and application as I discussed, we are targeting for the wearable devices. So it can be easily integrated with the wearable devices. Once it is implemented on the hardware, it will help the many such patients suffering from this. And for the future improvement in this model currently is still taking lots of parameters. It need to be encoded in certain different kind of compression technology that reduce further down to lower 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 sizes, so that it can be improved. And it can also improved by uh, in terms of compression efficiency. So you can see here before compression 99%, after compression it's compression reduces nearly around greater than 2%. So this is the overall work of mm, uh, this work is still in progress. So and if you look here you can this is the basically in the Google Colab, where we have coded all these models here. uh, so here you can see the we are here showing the we are taking the noisy signal, a clean signal, then we are adding a noise, and then we have the noise with our uh, proposed autoencoder. And you can see these two signals are a clean input and output are closely matched, and then the baseline bundle and the hair frequency are getting removed. So this is the denoising part, and here you can see the a detection deep learning CNN is here. You can see here this is having around 34 kilobytes of memory on device, just for 200 parameters. So we also optimize this one with help of pruning and all, and after that we find out the accuracy of, so it's near around 97 or 98. Mm. So that's all for this this presentation.